In Module 2 of this course, we looked at using DAWs, and we particularly looked at using them in conjunction with recording and editing and manipulating digital audio. In Module 3, we're going to turn our attention to MIDI and the very different ways that MIDI affords us to work with music inside of a DAW. In this first video, I want to talk about the basics of what MIDI actually is, why it exists, kind of the motivations for its creation many years ago, and how it differs from working with digital audio. So first, let's talk about what MIDI is. MIDI stands for Musical Instrument Digital Interface. It was developed around 1983 through a cooperation amongst many of the major music technology hardware manufacturers at the time. And they all got together and developed this specification over the course of a couple of years. It's a standard protocol that allows different devices made by different manufacturers to communicate with each other. Nowadays, a lot of times that means different software programs, but it also it originated as a hardware protocol with cables, and there are still MIDI devices that are pieces of hardware that communicate over MIDI cables. And so the important thing is that MIDI is really this protocol of how these devices or these software programs or whatever they might be are able to communicate with each other and exchange information. And it's a note-based protocol or an event-based protocol. So unlike digital audio that's storing a bunch of amplitude values describing how a waveform is changing tens of thousands of times a second, this is encapsulating every note in a piece of music with a particular set of information to describe that note, like the pitch that was played, the velocity with which it was played, how hard the note was hit, things like that. And then there's a lot of other parts of MIDI they can bring in other kind of ancillary, more kind of expressive information or other kinds of data. So that's the basics of MIDI, and it's obviously been with us for a while, so it's been successful as a protocol. I want to talk about why it emerged and why we still have it here with us today. In the early 80s, when MIDI was developed, there was a real problem in that musicians would have a bunch of different pieces of hardware to make music. They'd have keyboards that they could play on to play notes. They would have a bunch of different sound modules, and you can see them in this image here. That would be a sound module, that's a sound module, that's a sound module, and so on and so forth, all the way up. These are all different sound modules. And so they would want a way for all of these to work together to make music together, so that they could have, say, one keyboard that they could play, and that could activate music on each of these different sound modules. It could trigger notes on each of these different sound modules. Or they could have a sequencer and actually compose and record music that would play back through all these different sound modules. And each manufacturer had its own system to enable their devices to communicate with each other. But there was not a really good way for all these devices from different manufacturers to talk to each other. There were control voltages that could be sent between devices, but that had limited functionality and compatibility. And so MIDI really arose to solve this very simple problem that musicians in their studios had all this hardware from different manufacturers. They wanted to use it to make music together. And even the simplest notion of wanting to play a note on one keyboard from one company and have it trigger a sound on another one could be very difficult to accomplish. So MIDI solved this problem by having this common language that all of these devices could speak. And they would all communicate through this. This is a MIDI cable, and you can kind of see what it looks like. It's got five little pins there, and all these different devices would have ports to send and receive and sometimes pass through MIDI. We'll get into the details of that in the next video. So I want to emphasize here that the difference between audio and MIDI in terms of the way that it represents music. And to do that, I want to go back again. We looked before at these RPP files, the actual files that Reaper is saving on disk. And we talked about these when we were talking about non-destructive editing and how they weren't actually storing any amplitude values or any audio data inside of these files, but rather when we had an audio track, we were getting a reference to a source file, a wave file that exists someplace else on the disk, and then some other information about kind of where that's placed and different ways about how it exists on a particular track inside of a Reaper, inside of the DAW. but the actual audio information is all stored inside of that WAV file. So audio, again, and we know this also from this waveform over here, is this collection of amplitude readings stored over time. That's how it's represented on disk. MIDI is a very different situation here. With MIDI, there's no reference to an external file here in this RPP file. This is the actual MIDI data here that we're looking at. And I don't expect you to read that and understand what it means. But each of these lines is basically referring to a single MIDI event, like a note being turned on or turned off or something like that. We can see how compact this representation is. These are hexadecimal numbers here, so it's a kind of a shorthand way of representing a bunch of binary digits. But the point is that we're representing an entire note, everything about that note, through just a small number of binary digits. It's not tens of thousands of bits per second that we're recording here. It's just a handful of bits to represent an entire note that might last several seconds. So we have this more abstract kind of symbolic level of data that we're looking at. And we can see this in the DAW as well. If you look over here, you can see how MIDI data is represented. It's not represented as a waveform anymore, but each of these is actually a note. Each of these is representing a note. And we can see its start time and its stop time. We can see what pitch it is by how high or low it is. So we have time on our x-axis, and we have pitch on our y-axis there. So we see this represented in a much kind of more abstract and symbolic form than we would see with an audio waveform. We can look at this and immediately understand some things about the MIDI that exists on that track. So I want to emphasize these differences a little bit more. So I put together this little table to try to summarize these. We already talked about how MIDI is event or note-based, whereas audio is sample-based. And that's what I tried to show you in the last couple slides. This obviously has implications for the amount of storage space that's required to store information. An entire MIDI song, a 3-minute song or something, might only take up maybe 5 kilobytes of data if you're saving it as a MIDI file, whereas the same thing in audio might be 3 megabytes or something if I was saving it as an MP3 file. So there's very different implications in terms of data size. Obviously, these different formats are better suited to different kinds of things. MIDI, as we saw, was a highly structured representation of musical data that represents music as a series of notes that are played at particular pitches, that are played at particular attack velocities, and so on and so forth. And so that might be very good for representing certain things, like playing a piano keyboard. It might be very bad at representing other things, like very unique timbres and how they're changing over time, or even how a string player might start a note at pianissimo, really quiet, and then gradually crescendo over time. That's possible to represent with MIDI, but actually much more difficult than representing, say, a piano note where I just hit it and then let it decay. Audio obviously can represent any sound very easily because it makes far fewer assumptions about what it's trying to represent. It's just basically looking at the waveform and trying to represent that. So there are situations where MIDI is more appropriate, and there are situations where audio is more appropriate. And also, as a consequence of this structured format versus this more open format, with MIDI, it's extremely easy to edit individual events. As you saw in that view I had on the last slide, this one right here, you can imagine just going in and dragging one of these notes and changing it, and not changing anything else about the music. So you can go in and change properties of these individual things because they're just encoded as these MIDI messages. With audio, that's much harder to do. I might be able to change the amplitude of my waveform as a whole by creating an amplitude envelope or something like that. If I went in, say with a chord like this, it's just a C major chord there, a C, E, and G. In MIDI, if I wanted to change that E to an F, I could just go and edit the data, and I'd end up with this. But if I wanted to do that, and that was all recorded on a single audio track, that would be extremely hard to do, to just separate that E out from the C and the G and change it to an F. Very hard to do in audio, very, very easy to do in MIDI. So again, there's There's situations where MIDI makes a lot of sense because of how we want to represent our data or how we want to store it or how we want to be able to edit it. And there's places where really audio is the only thing that can effectively represent the music that we're trying to express. So to review here, what we've covered in this video is what MIDI is and how it is different from digital audio. In the next video, I want to talk about different kinds of MIDI devices and what they do and how they communicate with each other.